This is Knowledge Engineering with Semantic Web Technology. Welcome to the second extra part of this lecture number 3, Ontologies and Logic. And in this part of the lecture, we want to talk about another automatic reasoning algorithm, which is called the resolution. And we want to do this for first-order logic. You might remember we have always learned about some automatic reasoning algorithms for the Tableau algorithm, and we did this for propositional logic, first-order logic, as well as for description logics. And the resolution algorithm we will see in propositional logic as well as in first-order logic. So, what is resolution? Yeah, it's a simple algorithm based on deduction rules, and it is a special form of enumeration, as we will see. And it follows exactly the same principle as the already known Tableau algorithm. So instead of proving that a formula is a tautology, so that it's always true, it deducts a logical contradiction from its negation. So this simply means if we have a theory or a knowledge base and we want to prove that f sub 0 is a logical consequence of that knowledge base, so what we do is simply we say, or we have to show that, of course, all the logical expressions within the knowledge base, they imply f sub 0. And this expression is a tautology. And, of course, to do this, we have to show that its negation is a contradiction. And to do this, we have first to transform this expression into a canonical form. And we know already this canonical form for the resolution that we need is the so-called conjunctive normal form. Therefore, you see here all these conjunctions, and this is nothing else but the clausal form. So the resolution procedure allows the entailment of a contradiction from a knowledge base given in a clausal form. So let's talk about the basic principle, and we start, of course, with propositional logic. So in propositional logic, we always are dealing here now with conjunctive normal forms for the resolution. So this means you are looking here at a clausal form, which consists of a conjunction of two clauses, and the two clauses itself, they are disjunctions. So if we have the same variable in both parts here of this clause, so if we have it once negated and once not negated, then of course one of both must be wrong. Either P is wrong or not P is wrong. This is quite clear. So the other way around, if the original expression really is true and we know one of the both, P or not P, must be wrong, this means that definitely at least one of the other literals within these two clauses must be true. Otherwise, it would not compute true. So this, of course, is the basic principle. And this means that, of course, the expression, the disjunction of all the other literals, again, must be true, because at least one of them is true. So this is the basic principle. If you turn it around, you could say, okay, therefore, if this original proposition is a contradiction, so if this disjunction of all these literals is a contradiction, then of course also if I extend this disjunction in the way you see here with one and the same literal, one's negated, one not negated, this then is also a contradiction. So think about it a little bit, but you will see this is clearly true. And of course, we can make use of that principle. Now you might ask, yeah, so what is it useful for? You will see it on the next slide. So if we have in a clause, for example, twice or in two of its clauses, the same variable, once negated, one not negated, we can substitute these two clauses. We can transform it into a new clause, which then does not contain this original variable. So it means we shrink somehow the information in there, because we can remove variables which are as well negated and not negated in two of the clauses. And this might in the end somehow lead to a situation where we only have in two clauses one atom, which once is negated and on the other hand is not negated. And this would resolute in a so-called empty clause. And then, of course, we are done. Then the logical formula from the beginning is resolved, and we have deduced that there is a contradiction in it. So, and this was our original goal. We wanted to show that there is a contradiction because we made somehow logical equivalence transformation on basis of this algorithm resolution principle, and with that, in the end, you are trying to deduce a contradiction. That was our primary goal. So how does it work? Resolution for propositional logic, how to deduce a contradiction from a set of clauses. So simply we select two clauses from our knowledge base M or from our theory M and create a new clause K via a resolution step. So if this clause K is empty, then a contradiction has been found. If it's not empty, then K, of course, is added to our original knowledge base, and we continue with step 1. Of course, you have to prove, this is a syntactic method, you have to prove for this so-called resolution calculus for propositional logic that it is correct and complete, because this again is a syntactic method which is used to show semantic computations or semantic interpretations. So therefore, correctness and completeness has to be shown. We have talked about that in the previous parts of the lecture. So, how to prove that the formula psi is a logical consequence of a knowledge base of a theory phi of clauses. So first what we have to do, we of course, we know resolution is a proof by refutation, therefore we have to compute the negation of this implication, which is or which should be then a contradiction. So you see here, this phi implies psi will be logically transformed into phi and not psi. So what we then do is we have to determine the according clausal form of this logical expression, and then we select two clauses from our newly extended knowledge base and create a new clause K via our known resolution step. And then again, if K is empty, then a contradiction has been found and it holds that our original assumption was true. So psi can be logically deduced or entailed from phi. On the other hand, if K is not empty, then K is added to the set and to our knowledge base, and we continue here with step 3, which means we select new clauses. So this is the basic resolution algorithm for showing that we can prove the correctness of a logical consequence. So let's do an example on that. So first of all, we have a knowledge base. So for example, we have the following assumptions or propositions in our knowledge base. If it rains, Jane brings her umbrella. So we design or represent this as R implies U. Then if Jane has an umbrella, she doesn't get wet. So this would be U implies not W. And if it doesn't rain, Jane doesn't get wet. So not R implies not W. So what we want to prove now is Jane doesn't get wet. So this would be the formula we have to prove. So first of all, we have to transform our knowledge base into clausal form. That's pretty easy. So we substitute all the implication with a logical equivalent disjunction, and this then is our simple clausal form. So in the first, we have not RU, in the second, we have not U, not W, and the third clause would be R and not W. So then we add the negated formula to our knowledge base. So we want to prove that Jane doesn't get wet, so we want to prove not W, and this will be again negated. We have double negation, so we can get rid of the negation. This is equivalent to W, and this will be added to the knowledge base. And the new knowledge base, you see this in the box below, consists of 4 clauses, which then are shown here. So this is our knowledge base, and from that, of course, we want to deduce this or there is a contradiction, because we have added the negative consequence that we want to show. So let's simply start. Let's have a look at that, and then we see, for example, W and not W, so the literal and its negation. The variable and its negation are in the following 2 formulas, for example, in 3 and 4. Therefore, 3 and 4 that you see here can be resolved to R, because W and not W can be resolved. So you remember that resolution algorithm. So we add R as a new clause to our knowledge base, and we continue. So then, for example, we could continue with number 2 and number 4, which both contain W and not W, which can be again resolved and resolves in a new clause, number 6, which will be not U. So we add not U to our knowledge base. So now it would be nice to get a new variable which would lead somehow to a termination of the process. And to do this, we could see here, or we can see this rather easily, we should choose number 1 and number 5, which contain R and not R. So therefore, from that can be resolved U. And then if we add U simply to the knowledge base, we see here number 6 and number 7 is U and not U, so 2 atomic expressions, and we have found a contradiction because this resolves to an empty clause. Therefore, our original assumption holds. It means Jane doesn't get wet. So this was quite easy, wasn't it? Okay. Of course, it can be much more difficult if you are dealing with more difficult expressions. And the point is, of course, if you then also deal with a complexer kind of logic, like first-order logic, the situation gets even more complicated, simply because of the following reason. So consider the following 2 clauses in first-order logic. And now the question is, I see here variables, I see here constants, I see here predicates and functions. And the problem is, how can I resolve that if it's not really exactly the same or the negation of it in the other formula? So what you have to do here is you have to apply so-called substitutions to be able to resolve a formula like that. So what you could do, for example, you could resolve a variable with a constant, for example. Or you could also transform or substitute a variable with a function over another variable. This is allowed. So there are specific rules, which are the so-called unification rules for substitution, and we will talk about this soon after. So what you can do here, for example, is you can substitute in the first clause the variable x with a constant a that you see in the second clause. And what you then can do in the second clause, you could substitute the variable z with a function f of y. So then this would resolve then in the end, because here the first part of the clause would be once an expression and its negation, and this resolves then to the lower part of the formula. But of course you have to take care to make everywhere this substitution. So it means every occurrence of x, also in the f of x, has to substitute it by the constant a, and every occurrence of z has to be substituted by y, f of y. So this would be the resolution for first-order logic. Now let's have a look how this really works, and for this we have to talk about unification of terms. So this kind of substitution algorithm that we have seen. So unification means we have 2 different literals within a term, and somehow a variable substitution sigma should be applied on these 2 terms, L sub 1 and L sub 2. That, of course, both expressions, again with this substitution, compute exactly the same. So, and if there is such a variable substitution sigma, then sigma is called a so-called unifier of L sub 1 and L sub 2. And we want now to see how this unification can be computed. So the unification algorithm works as follows. We have 2 literals, L sub 1 and L sub 2, and we are looking for a unifier sigma for these 2 literals. First case, if L sub 1 and L sub 2 are constants, then of course they can only be unified, or they are unifiable if they are exactly the same. I cannot substitute one constant by another constant. That's not possible. The interesting case is if L sub 1 is a variable and L sub 2 is an arbitrary term. Then it's unifiable if for variable L sub 1, the term L sub 2 can be substituted and variable L sub 1 does not occur in L sub 2. So this is the condition. The variable must not occur in the term that I use for the substitution, because otherwise, this will blow, or this will break this construction. So this is quite easy. If 1 is a variable, I can substitute the variable with an arbitrary expression. But I have to take care that this arbitrary expression does not contain this variable I am substituting. Then we have a third case, that L sub 1 and L sub 2 are predicates of functions. So they are here denoted as PL sub 1 and PL sub 2 over, of course, a bunch of more primitive expressions. And they are only unifiable either if both of them are exactly the same, Or the arity of both must be the same, so n must equal m, so the indices must be the same number, so both of the predicates should be applied to the same number of variables. And then all the terms which are inside these predicates, they must be unifiable with a term of the other expression. Only then we can make here a unification. So let's look at a few examples. I have here a table with a few examples. Let's go through them step by step. So if we look at the first one, we have first an expression over a predicate over two variables, and then the second one is a predicate over two constants. And this is quite simple. If we substitute variable x with constant a, then of course it's unifiable, then they are both the same. On the second one, you see it's much more difficult. So because in first place we have two variables, which is the same variable exactly, and in the second one we have two constants which are different. So I can either do a substitution x substitute with a or x substitute with b, but not both. So this is not applicable, this is not possible. Look at the third one. We have two different variables in the first expression, x and y, and we have in the second one two different variables. So this is easy. I substitute x with a and I substitute y with b. Then both are the same and they are unifiable. So the fourth one, we have again two variables, x and y, and now in the second one we have both times the same constant. This is also possible. Of course, I can substitute variable x with constant a, and I can substitute variable y with constant a. This works, no problem. The next one is a little bit more complicated. We have a predicate that has as the first argument a function over the variable x, and as the second argument a constant b. And then we have a second predicate, so in L sub 2, which has as first argument a function over a constant and as second argument a variable. So what we can substitute inside here, first of course, are the variables. We can substitute the variable x with a constant z. So then the first expression in both of the terms is identical. And then for the second one, we can substitute the variable z with the constant b. So then also the second part of the term is identical. So let's look at the next one. Again, we have in the first one first a variable x and then a function over variable x, and then in the second one we have two variables y and z. So this again is possible to substitute it. So first I can substitute x with y, so this has to apply it everywhere. So also the second expression then will become f of y instead f of x. So and what I can then substitute is I can substitute in the second expression the variable z with f of y, and then both are again unified. So this is the same. The only thing that does not work, for example, is the second one. If I consider the same first expression and then in the second expression I have twice the same variable, yeah, we have here the same problem. You will see that it's not possible to find a suitable unification, and you should think why this is the case at home. But it's not possible, I can tell you. Okay, so this is unification. And we have to apply this kind of unification to be able to do a resolution for first-order logic. And we do this first, or we learn this with the help of a suitable example. So in first-order logic, again, we can consider a knowledge base, which consists of a T-box, where we have some axioms and we have some assertional knowledge. So here, for example, we say that every human, if x is a human, then there must exist some y, which is the parent of x. So this is quite simple and clear, the first axiom. Second axiom, for all x, it holds, if x is an orphan, then and only then x is a human and all parents of x are not alive. So this is also clear. So we have two axioms and then we apply this on individuals. We say, okay, we have one orphan, Harry Potter is an orphan, and we say James Potter is the parent of Harry Potter. And now the question is, can we automatically deduce from that knowledge that we have here that James Potter isn't alive anymore? So let's try. So what we have to prove is simply if we can deduce that James Potter is not alive, so we have an implication here, and we simply connect all of the knowledge we have in a conjunctive way and then try to imply our statement that we want to prove, so that James Potter is not alive. And this expression should be a tautology. So this is in the same way like for propositional logic. So we know resolution works the other way around, so we have to negate everything. So the negation of the entire expression must be a contradiction. Okay, so far so good. To apply the resolution algorithm, everything has to be in clausal normal form. So therefore, we have to do lots of translation. You see here first a few steps to get to the so-called negation normal form and then prenext normal form. I have left out the steps, you can compute it at home. And then from this prenext normal form, we have to get to the conjunctive normal form, which over a few steps then will look like something like you see here. So this is then a clausal form, conjunctive normal form, a conjunction over disjunctions. And for better readability, of course, we write it then in the way we are used to write clauses. And you see here our knowledge base then consists of these 8 clauses that we have here. And what we do now, we try to find 2 clauses where we can apply a new resolution step. And of course, you have to take care a little bit more at first order logic, because you have also to identify possible substitutions to make 2 clauses resolvable. So what we have here, for example, we can look at clause number 3. There we have not often x1 and not parent of y1 x1 and not alive y1. And we can look at number 7, where we have also parent of, but this time not negated, with 2 individuals, James Potter and Harry Potter. And what we simply can do here, we can substitute the variables in number 3, which is x1 with Harry Potter and y1 with James Potter. And then, of course, we could resolute this, which would, in the end, we have at every place do this substitution, end in a new clause which says not often Harry Potter and not alive James Potter. And this clause number 9 then would be added to our knowledge base. And we see here, if we look at number 9 and number 8, so we have here once alive and not alive. Of course, this is a quite simple substitution or a resolution, because this resolutes in not often Harry Potter, which is number 10, which would then be again part of our knowledge base. And maybe you see it already here. Number 10 and number 6 are once the negation of the other. So what we can do here is we can resolve an empty clause. And you see we are done. And we have shown that our original assumption, which was that James Potter isn't alive anymore, is true. So it's as easy as that. This is the resolution for first order logic. In general, if resolution is applied to a contradictory set of clauses, then there exists a finite number of resolution steps to detect the contradiction. And the number, of course, can be quite large, and there is not a given order in which you have to apply this to make a proof which is as short as possible. So this is a little bit difficult and a little bit, at random. So you have to choose which resolution steps to take to get to an end. The point is, in first order logic, resolution is undecidable. It means if the set of clauses is not contradictory, then the termination of the resolution is not always guaranteed. So this was one of the last parts of logic that I wanted to give you an overview of. So we have learned about another resolution algorithm. In the last extra part of the lecture, I give you a short or a brief history of the general notion of ontology in philosophy and computer science.